Good morning, everyone. It's my honor to be introducing this morning's lecturer, Professor Stanley Chang. Professor Chang is the Mildred Lane Kemper Professor of Mathematics. He's completed his bachelor's degree from the University of California, Berkeley, his master's from the University of Cambridge, and a PhD from the University of Chicago. His research is based on the positive scalar curvature and rigidity of manifolds, non-commutative geometry, and tools of surgery theory. At Wellesley, Professor Chang teaches a wide variety of courses at all levels of the math curriculum, including calculus, linear algebra, abstract algebra, real and complex analysis, and topology, to name just a few. He has served on the Academic Planning Committee and Presidential Search Committee in 2016. Through these involvements, Professor Chang shows his interest in helping college maintain a high academic standards for all of its students. Professor Chang has co-created the Wellesley Emerging Scholars Initiative in the hope of increasing participation of underrepresented minorities in the mathematical sciences. Today, Professor Chang will be talking to us about how mathematics can help us shape policy. Without further ado, please join me in welcoming Professor Chang.
So good morning, everybody, and thank you very much for inviting me here. It's a privilege to speak to you. So in the next hour or so, we're going to be talking about some mathematics. I'm actually going to make you do I'm going to get you to think about some mathematics. But my message to you is that in this day and age, in order to be good social policy makers, you have to understand a little bit about mathematics and how it affects the lives of everybody. Okay? So I think that the classical view of mathematics is the following, that we have a world, okay? And the world is filled with certain things. And then we have math, which is filled with other things, okay? And so the intersection of the two includes some Einstein's equation, E equals mc squared, the gravitational equation, PV equals nRT, which is how gases behave in chemistry, F equals ma, which is force equals mass times acceleration. Now, you see all of these things seem to exclude all of these things. And in this conversation, I will try to make this intersection bigger by showing you how politics, economics, human relationships, and even war has to do with mathematics. Okay. Now, in this talk, I'm going to be focusing on 4 primary things and some smaller things afterwards. The 4 things I'm going to talk about are cryptosystems, population control, disease spread, and weather phenomena. I think all of these things are important to us and affect our daily lives as well as the lives of the generations that come after us. So let me talk about cryptosystems first. Of course, we've heard a lot in the news about the problems of hacking, the problems of stealing information. Perhaps it all snowballed from Edward Snowden a few years ago, who exposed that the NSA, the National Security Agency of the US, have been spying on not just other world leaders, but of American citizens themselves. Computers, drive our world right now. It can affect major things like presidential elections. And it's important for us to know how computer systems work and what the state of mathematics in, for example, security is going to take shape. Okay? So what I want to talk about first are ancient ciphers. Okay? So ancient ciphers are ways of embedding information using some kind of mathematics. So for example, you could have an alphabet shift by 3 spaces, and then you can write your message with the alphabet 3 spaces away from what you really mean. And then the receiver of this will just take 3 spaces to the other side and then decode the message, right? So ancient ciphers, or ciphers in general, are a way of applying some kind of mathematical or numerical principle to language, okay? So it's the relationship of the two that gives us the idea of coding, okay? And that's exactly what cryptosystems do. Now, I should mention that crypto systems were vital in, for example, World War I, World War II. Recently, as we recall, the Navajo Indians, or Native Americans who were honored at the White House, had actually a very, very vital role in World War II. Because the Navajo language was so complicated that Germans could not actually intercept and translate them. I mean, it's actually scary to think that the Germans actually did study other Native American languages for this exact purpose, but the Navajo language was so unique and so strange that they couldn't get anybody to understand it, right? So, so on the communication side, it's absolutely vital that you have some kind of system that can be decrypted and encrypted. So for example, the notion of symmetric cryptography works as follows. You have a plain text, which is the message that you want to send. The process of encryption requires that you have some kind of key. So the key is a cipher, it's a method, it's an algorithm, okay? And the algorithm gives you some kind of ciphertext, which looks like garbage, right? But in fact, encodes all the information in here without any loss of information, right? Decryption, right, means that you receive the ciphertext and you have your unalgorithm, right, that undoes what the algorithm here did, and then it returns the original plain text to you. Yeah. Now, this is called symmetric because both the sender and the receiver have to use a certain kind of key, and you have to agree beforehand what key you're going to use. Okay? So somebody has to say, here's my key and here's your key, and this is the way you use it. Okay? Now, this is not terribly useful in, for example, transactions on the internet where people don't even know each other, or if you're buying something from Amazon, you don't know who's on the other end of Amazon, so how are you going to know what key to use, right? So we have this thing called asymmetric cryptography, which I will describe in a moment. So in this case, I have original data. This is my plain text, okay? Now there's this thing called a public key, and there's this thing called a private key, okay? A private key was what the people had in the previous slide, okay? Their keys are private. So this part should be understandable to everybody, okay? This part is the thing that's not clear. What does it mean to be a public key, all right? And I will describe in the next few slides exactly why public keys are exactly the correct things to use. So here comes the math, right? So a prime number is a number whose only factors are itself and 1, okay? So for example, the number 5 cannot be broken as a product of 2 other numbers except 5 times 1, okay? So a list of primes can be generated, well, Euclid showed in 300 BC that for any collection of primes that you write down, you can find another one. So that means that the list of primes is actually infinite. Okay, so there are always more primes that you can look for. Now, primes do not satisfy any kind of pattern. There's no kind of formula that generates all prime numbers. Okay, but there are lots of questions that you can ask about primes that are still not resolved. For example, you notice that there are primes that are 2 apart, like 5 and 7, 11, 13, 17, 9, 59, 61, okay? But 197, 191, 99. You see that they differ by 2, okay? So one of the most important conjectures in number theory is that there are infinitely many of these pairs, right? So does that make sense? Okay? So here we saw like 5 of them, right? But the conjecture is they never end. There's infinitely many of them. And this conjecture has been around for 300 years and nobody can solve it, okay? So prime numbers are of extreme interest to people, okay? So let me talk about what a semi-prime is, okay? Now a semi-prime is something that's almost a prime but not, okay? So for example, 35 is a semi-prime because it is a product of exactly 2 prime numbers, 5 times 7, okay? So 35 is a semi-prime, okay? It has 2 prime factors. If it has any more than 2 factors, right, it's not a semi-prime. So for example, 41 and 61 are both prime. This gives you 2501. So 2501 is a semi-prime. Okay? So semi-primes get big. Okay? So notice, for example, that if I have a one-digit number with a one-digit number, I get a two-digit number. Okay? If I have a two-digit number times a two-digit number, I get a four-digit number. And if I have a five-digit number with a five-digit number, I get a 10-digit number. Okay? So you might think that the digits just add. Well, here I have 3 digits and 3 digits, but I only have 5 digits here. 3 plus 3 is not 5, but it's approximately 5, 6, I mean. Okay? So generally what happens is that the number of digits that you have here times the number of digits that you have here, or instead of the sum of these numbers of digits gives you the digit of the semi-prime at the end. Okay? Now, if I gave you 35 and I asked you to factor it, you probably know from memory that it's just 5 times 7. Okay? If I asked you about 2501, you probably wouldn't be able to just do it in your head. You might want to use a calculator and figure it out. And if I give you this number right here, well, you would probably just write a script on a computer trying to figure out what these numbers are. Okay? So as the numbers get larger and larger and larger, the techniques that you use become more and more difficult. Okay? The RSA challenge, which is named RSA, is the initials of 3 computer scientists, formed a number of words, a number of things called the RSA numbers, and they formed this thing called the RSA challenge. So all of these represent numbers. So RSA 100, which we'll see in just a moment, is a 100-digit number. Okay? And RSA 110 is a 110-digit number. Now these are written in decimal. Okay? So notice that the numbers get bigger and bigger, but suddenly you have a 640. All right? This 640 is actually not a 640-digit decimal number. It's a 640-digit binary number. All right? So the number is only represented with zeros and ones. Okay? But for some reason, they called it that. The relationship between this binary number and a decimal number is about a factor of 3. Okay? So if you divide that by 3, you roughly get in this zone. Okay? So notice that some numbers, the numbers that you see in sequence, right, are all written in decimal, and then these weird ones right here are written in binary. But these numbers go in order, in magnitude. Okay? Now, what was the challenge? The challenge was to be given a number like RSA 100, okay, which has 100 digits, which someone somewhere sort of expect might be prime or semi-prime, okay? And the challenge is to factor it if you can, okay? To factor it if you can. Now, notice that writing down 100 digits doesn't seem like a big deal to you, okay? But there are only, the number of atoms in the universe can be written down in only 70 digits, okay? So this is the number of atoms in the universe, and for every billion, okay, if you had a billion universes, you would only increase the magnitude by 9 digits, okay? So the fact that you can even write down this number does not even describe how big this number actually is, okay? So you have to understand that these numbers, although you can probably, you can write this down in hand, but in 30 minutes, is actually larger than any conceivable thing that your brain can wrap your head around, okay? And the game is to try to factor it. And there was a prize that was given, right? A monetary prize for being able to do it. Now, a lot of these initial numbers were factored in the 90s and then early in the 2000s. In fact, for example, RSA 220, right, was only solved last year. Okay? So this 220-digit number was, by using supercomputers and a lot of geniuses in mathematics, is the product of this prime and this prime. Okay. Now, I'm trying to convey to you how difficult this is, and you might be asking yourself why this actually matters. I'll tell you in just a sec. Okay? So in 1999, right, cracking a 155 decimal number required 7 months with a supercomputer. Okay? And it was very, very expensive at that time. In 2015, it took 4 hours, okay, and $100 of computing time. So what's happening is that as computers get more and more sophisticated, these numbers become easier and easier to crack. Okay? However, even by today's standards, only about 2 columns worth have been cracked, and the other ones have not been. Okay. So the RSA challenge is still around. Okay? It doesn't have a monetary prize anymore. But breaking these primes is a way for us to understand how good our computer systems are. Okay? If you want to test how good is our current computer systems, the answer is try to break this number. And there's some way of thinking about these numbers as a measure or an index of the strength of our computer systems. So let me go back to this idea right here. Okay. Suppose you're buying something from Amazon. Okay? And the problem is that you do not want your information, your credit card information has to be sent from your computer to Amazon, and it may be intercepted along the way. Okay? How does Amazon keep your private numbers private? I mean, how does email remain private? How do people hack? How do people interpret what's happening when they intercept a message that's supposed to be encrypted? Okay. So this is the idea of public key cryptography. Okay. So when you want to buy something from Amazon, you type in and you press click. Amazon realizes that you clicked, and it sends you a number. That number is a semi-prime. Okay? The semi-prime has hundreds and hundreds and hundreds of digits. Okay? Now, this semi-prime has a factorization into 2 primes. But nobody knows it except for Amazon. Amazon knows that n, which is the huge, humongous semi-prime, can be broken down into p and q. But you don't, and you don't need to for the following reason. So Amazon sends you this number, which is humongous. Now, it may be intercepted along the way, but it turns out it doesn't matter. Okay? This number is called the public key. It can be intercepted, but it's so big that any interceptor does not know what to do with it. Okay? Now, this immense number takes this data on your computer and scrambles it. Okay? Now, when it scrambles it, it then gets sent back to Amazon. During this time, it can be intercepted again. Right? So there are 2 interception points. Right? One, where Amazon sends you the number, which is so big that nobody knows how to deal with it, and then back to Amazon with the scrambled data. And nobody knows what to do with that if they intercept it as well. Now, how do they decrypt? Well, they know the secret. They know this is the secret right here. This is their key. Okay? They know how to break apart n into p and q, and they use that by some algorithm to recover the original message. Okay? So the takeaway I want you to know about this thing is that public key cryptography works because numbers are really, really, really hard to factor. Okay? And even if you factored it, you may not know what to do with it. Okay? But the problem is that the factorization is very, very difficult. Okay? So let me describe to you what happens. Okay? We're going to look at public key length right here. Okay? So the idea right now is that we're in a race against the bad guys. Okay? So the good guys have to form some way of keeping things secure, and the bad guys are trying to hack it. Now, hacking it is easy if you have a great computer, and computers are getting better and better and better. So you have to make sure that your numbers are long enough that an interceptor cannot just use a desktop, okay, to crack it. Now, basically, at this moment right now, if I use a 124-digit number as my semi-prime, it is not recommended anymore. I mean, computers are so good that it can take a 124-digit number and probably crack it, in no time at all. Okay. At the present day, 2048 is our standard. So imagine a 2,048-digit number is coming into your computer and scrambling your data. That's what's happening right here. If you're top secret, right, you want to use something bigger, and in the future, you might have like a 15,000-digit number. Okay. So behind the scenes, when you're trying to send anything securely, there's mathematics going on behind you. Okay. And the race right now is to try to figure out how long a lock I need, right, to send out my message before somebody else can crack it. Now, there's a funny, there's a company called DigiCert. DigiCert is a security company, and it advertises to businesses to find ways of securing their data, okay? And this is what they say, okay? They can make your data so secure, okay, that at the present moment with one desktop, this is how long it will take, all right? This is their spiel, right? So it's going to have, so SSL certification is the method they use, and the universe is the second thing, okay? So the Big Bang happens, and your computer starts computing and trying to break this number, okay? So I can't read that, but here it says first galaxies formed, and you're still computing, okay? And then what does that say? Formation of the solar system, complex life forms, present day, is still computing. And ultimately, what happens is that the Big Bang ends, everything freezes, and the universe ends, and you're still computing, okay? So this is their way of saying, okay, you know, you can trust us with your stuff because it will take the length of, oh, by the way, and you're only 1/8 done, right? So by this point, you need 8 universes to be created and collapse in order for you to break this number that they're proposing for you, okay? Now, of course, this is a little bit cheeky because you're only using one desktop, all right? And this is sort of false advertising, I think, right? But the idea is that if you had like 1 million desktops or 1 billion desktops, you still can't do it, right? Well, the problem is that you can do it, okay? Because computers get more and more sophisticated. And so right now, you know, the NSA is sitting there with a lot of computer scientists and mathematicians trying to figure out what is the best way of keeping things secure, and that involves math. Here is a timeline, okay? So I want you to look at the asymmetric column right here, okay? An 816-digit number, right, should not be used for anything, okay? Like you can break it on your laptop in about 2 minutes, right? 1008, right, short-term protection against medium organizations. 1248, okay, very short-term protection against agencies, smallest general purpose level. 1776, okay, legacy standard level, protection from, I'm sorry, the previous one, protection from 2013 to 2015, and we're past that. Okay, so this is no good anymore. Okay, 1776 will get us to 2020. Okay, 2400 will get us to 2030. 3200 will get us to 2040, right? And then beyond that is just, it's just going to be very difficult. So behind the scenes, as we're sending things securely, this mathematics is happening behind the scenes. Okay, so hopefully I've convinced you that number theory is important in security systems, and it's difficult. Okay, I want to talk now about population. Okay, so sort of anecdotally, we talk about reaching a maximum that the planet can hold in population. There are all of these really frightening things that people and scientists have said about running out of food, running out of water, being deprived of resources, and huge cases of poverty and the end of our civilization. So wildfires, right, are caused by increased population density and other things. I mean, a lot of our problems these days arise because of population, right? The more people that you have, the more things they need, the more factories you have to create, the more pollution you get, okay? Nobody can live anywhere. I mean, it's actually kind of amazing that the state of Utah, for example, will double in size in the next, say, 25 or 30 years, okay? So places that we think are fairly small compared to, say, Boston or New York are becoming overwhelmingly large, okay? Of course, we know about healthcare. Healthcare costs are immense, and we'll talk about health in a little bit. And even things like gun violence, right? So when you have dense populations, you have dense congregations of people. right? You have people in very, very dense areas, and that makes mass shootings much easier, right? So the density of people, the proliferation of people is going to be a huge factor in all of these things. Now, there's a lot of mathematics behind the population growth modeling, okay? So I'm going to talk about modeling in just a moment, but we hear these words like exponential, right? Or geometric or arithmetic as ways that things grow. So hopefully I'm going to tell you what those things mean, okay? And I'll also tell you that the things that you studied in calculus and maybe in trigonometry and algebra are actually used in real life. You just don't know it, okay? Because nobody ever told you, okay? So here's how things work, okay? Suppose you have a population, all right? And only 3 people are born every year, okay? That's going to be very, very slow growth. It's going to be growth, but it's going to be very slow. So if only 3 people are born every year, that's called arithmetic. Okay? And so your population will grow linearly as a result of time. Okay? But you hear that that's not the case. Okay? Populations go exponentially. Now, what does exponentially mean? Okay. So what it means is that it's actually very, very slow at the beginning. Okay? And then it starts to increase, but it starts increasing really, really fast. Okay? And that's sort of what we think of as exponential. When people say things like, oh, everything's getting exponentially bigger, let me explain what exponentially bigger means. Okay? So there was a mathematician named Malthus, okay? And he created this thing called the Malthus law of population growth, right? And this is what it is. So the Malthusian law of population growth says the following. If you are a small population, okay, and you're in a certain location, you're not going to bump into each other all that often, okay? So given the fact that you have to bump into each other to reproduce, right, there's not going to be a lot of reproduction going on when there are very, very few people. Now, when you have a lot of people, the chances that you're going to bump into someone is going to be very high, right? So when you bump into someone, you automatically reproduce, right? And then you make the population bigger. So the rate at which the population grows, okay, is proportional to the amount of people in the population. So the more people in the population, the faster you're growing because your chances of reproducing with somebody next to you is larger, okay? So that's why exponential goes very, very slow at the beginning. You're not bumping into each other. There's no collision, okay? And so as a result, your initial growth is very, very, very slow. But then at some point, when you reach some kind of critical mass, population starts going up. And as it goes up, it gets further up. Okay, so that's exactly how it works. Now, the thing is, the world doesn't work that way, right? What happens at some point is that you're going to run out of resources. Now, if we lived on a humongous planet with infinite resources, then our population would be just growing exponentially for a really long time, okay? However, if you collide into each other too much, all right, you are eventually going to fight for resources, okay? You're going to be fighting for water. You're going to be fighting for standards of living. You're going to be fighting for housing. You're fighting for everything, okay? So in actuality, what happens with most populations when they have some kind of resource restrictions or geographic restrictions placed on them is that there is a minus term. Okay? So this first term right here tells you I'm going to grow because I'm reproducing. But this minus sign is a term that says if I grow too much and if I keep colliding into people, then I'm going to have a negative effect. This gives us this thing called the logistic growth model. Okay? The logistic growth model has a few pieces, and this is what happens when you fight for resources. There is a very, very slow section in the front. This is called the lag phase. Now, as you start increasing right here, you notice that you're sort of exponential. Okay? So exponential growth happens here. At some point, you reach this thing called the critical value. Now, what is the critical value? If you remember any mathematics, notice that this part right here is concave up. This part right here is concave down, okay? Even though we're increasing, okay, so our first derivative is always positive. Here, the second derivative is positive, and the second derivative here is negative, okay? So this is a turning point where people start realizing, okay, something happens here, and this is called the deceleration phase. Okay? The equilibrium phase is a phase at which you reach some kind of plateau, that your death rate and your birth rate are the same. Okay? And this is called the carrying capacity of this system. Okay? Now, it's much more likely that this is what we're going to experience. And we'll see a graph later about how the human population actually looks. But any population, animal populations, plant populations, bacteria populations, they all have this feature. Okay. Another way that the growth model can be modified is that you have some kind of logistic growth. Instead of flattening out, okay, you have this kind of wavy behavior. This means that you overconsume, okay, then you die. Then you release some resources, so you overconsume again, and then you die. So then there's this sine wave happening here, which is why we study trigonometry. Lots of things in life are cyclical in nature. For example, your mood throughout the day is cyclical. You know, you're crabby in the morning, you feel better at night, and it rotates like this. The temperature of a point on the planet during a 24-hour cycle is going to get hotter and hotter and hotter, and then it's going to get cooler and cooler and cooler at night. A lot of physical systems are, a lot of chemical systems in your body are repetitive like this. This kind of behavior is called sinusoidal. Okay, sinusoidal. Just a little bit of a Greek lesson, Latin lesson for you. The word sinusoidal comes from two pieces. It's sinus and it's oidal. Okay? Now, oidal means in the likeness of. Okay? Like humanoid means in the likeness of a human. What's an asteroid? A likeness of a aster, of a star. Okay? Android, in the likeness of a man. Okay? So sinusoidal means in the likeness of your sinus. Okay? Now, what does sinus come from? Sinus is actually a word that doesn't mean the stuff in your nose. Sinus actually meant the shape that a beach or a bay has near the ocean. Okay? It also means the crook of your arm when you're holding your baby. That's also called a sinus, okay? Or a sinus. So a sinus, right, is anything that actually has a cragged, wavy pattern. And that's where we get the word sine and cosine, okay? All right, so a logistic growth model is one model of human population that we'll be seeing in just a moment. Okay, so here's the population of the Earth. Okay, as you see right here, right, we were very, very flat for a while, right? Around 1927, we start increasing in population. You notice here, right, that we are concave up. Our derivative is still positive, but it's getting much faster. The critical point, do you see the critical point? It's around 1987, okay, which was probably before you were born, okay? But at this point right here, there seems to be a sort of a shift in the population, and the population is starting to steady out, okay? So we know that various populations, like I think that China's one-child policy, you know, or Japan's declining population have something to do with the fact that we're increasing, but we're increasing much more slowly, okay? Now, if we believe that our planet can only sustain about 9 billion people, then in 2048, we're going to be reaching our carrying capacity, okay? And that is in your lifetime. That might be in my lifetime, okay? But it'll certainly be in your children's lifetime, okay? So at this point, what's going to happen if we're not really careful and we don't plan is that there's going to be the same, I mean, if you can imagine, the death rate and the birth rate will be the same. And if you think about death rate these days, right, people are living longer and longer because of medicine. So the death rate is not, I mean, from our point of view, it's not that high. But if you consider a time when the death rate, which is not that high, gets higher enough to overcome the birth rate, it's going to be a really, really scary time. Okay. There are lots of scary things happening. I mean, in California, they were thinking during their drought, they were thinking about going into this crevice in the middle of the earth where the water has been undisturbed for 25,000 years. Okay? So as desperation sets in, you're going to see this kind of, not to scare you, okay? But this whole thing is supposed to be a way of, I mean, the world is scary right now, right? And I think we need to acknowledge that there are lots of different ways that we can help to solve this problem. As you probably know, a few weeks ago, the White House obliterated the HIV/AIDS Presidential Council by FedEx. And this commission was established by Bill Clinton in 1991. It was renewed under the first Bush. And then it stayed around. It contained lots of very prominent doctors, scientists, epidemiologists. And because of the White House's view towards health reform, 6 of them resigned in June, okay? And then the other ones were fired a couple weeks ago, okay? So the spread of disease is a really big issue as more and more people become sick, and the cost of managing their sickness becomes greater and greater. One of the first mathematical ways of dealing with disease spread was actually for gonorrhea, okay? In gonorrhea, there was a behavior, okay, some behavior in the 50s to the 70s that scientists could not explain, okay? Of course, everybody tries to model disease, but somehow gonorrhea was one of those subjects that was just really, really, really hard to understand. And the thing that was really, really hard to understand was actually a social thing. It turns out that once scientists and the scientific community realized that there were gay people and there were straight people, and they behaved in very, very different ways socially, then they figured it out. So mathematics can actually be difficult to implement unless you know and are willing to admit that there are people in the population who are different from you, okay? So once they figured out that men spread gonorrhea to men or women at different rates, okay, that women spread gonorrhea to men and women in different rates, then you can write out the equations and you can figure out what happened. And that's exactly what they did, okay? Let me explain to you how disease is modeled, okay? It's really interesting. Suppose you have a disease, okay, that is reinfectable, meaning that if you have the disease, you will not become immune to the disease once you are cured, okay? So there are four, okay, groups of people, okay? So here are the recovered people, okay? Here are the infected people. Here are the exposed people. I just remember what E was. That's why I went backwards, because I forgot.